Applied Dynamics. Dynamic Systems, I'm sorry. He's from North Carolina. He was here at the 84 Symposium and gave an excellent presentation, which I found very inspiring and contributed a lot to the article I wrote in the Tesla Journal that appeared back in January. So he's done quite a bit from his North Carolina base there. He's been working on Tesla projects for years and years. So here's Charles Yost. Tie clip or no tie?
Is this a speaker?
This is the microphone for tape recording.
Oh.
That's why we want you to repeat the questions.
Okay.
Okay.
I need to find out how I sound here. I'm a soft speaker and I don't even realize it.
We can pull that out of the stand.
Okay.
There you go.
If I can hear myself, I figure that's the way I sound. So I can hear myself. Any problem out there on that? Okay. Well, my topic is really it's an investigation of concentric electric field generators. The classic one, of course, is the Faraday generator. That's not specifically the one that I'm investigating. I'm looking at very high voltage generators that are more akin to what people have started to see as the Searle generator, which of course came from England. The reason I'm interested in this is because I've had a long time interest in the development of an electrical spacecraft, and as near as I can tell, it's going to require some pretty fancy tricks with not only high voltages, but of course magnetic fields and things of that sort, since I'm looking at it as a primary propulsion system. The Faraday disk seems to be fairly well entwined with the Searle generator, and you might even look at some of the Tesla techniques, because there's pulsing going on of magnetic fields in the Searle generator. I don't know too much about it, just like everyone else. I suppose one of the differences about that is that I am an experimenter, and I do set up experiments to check out different ideas. And of course there's a lot of ideas expressed in the literature about Searle. And we're going to get into some of the findings that I've personally made in investigating different ways of producing voltages from rotating disk. Another part of my purpose in being here is to really get in touch with other people that might be familiar with this field, doing work in this field, and perhaps we can share our findings and efforts in that respect. I'm going to show you on this projector over here just a couple of business cards. I don't know how you work this thing. Got a switch on here. That didn't do much. And there, big switch. There we go. I'm going to give you some background about myself. I know a lot of you here, probably this is the first thing you've ever seen of me in my life. I have a company, Dynamic Systems. That's who I work for. I thought it was my company until I hired a few people and found out I couldn't really do as I pleased anymore. But I also have another activity you can see up there. I think it's important to have some kind of publication on electrical spacecraft networking, reporting of some variety. And so, for starters at least, I'm willing to act as a home base and do things. I have people that can do things. My own background, and I noticed in Japan, I've done some work with people in Japan. One of the first things they always do is they tell you who they are, where they work, and when they were born. So I'll tell you when I was born. Might as well know that. I was born July 10th, 1933, and I've been pretty much fascinated with the Tesla material since the age of 14. That came out of reading The Prodigal Genius by John J. O'Neill. And of course that's about 1947. That's when the UFO flaps started, so that just enhanced my interest. And probably is why I got into the spacecraft, into this thing. And by 1950 and 51 I was making 10-inch reflector telescopes and solid rockets and Tesla coils, of course. And 52 I made a large Van de Graaff with a 20-inch ball, about 7 feet tall. It was a little different in that for that size it was self-starting, meaning it was a totally frictional machine. Didn't use any booster transformers. Sure surprised me when it started up. I met Townsend Brown that same year in Los Angeles and saw his disc, his flying saucers on a maypole. And that was in 1952 already. He had these saucers on a maypole and applied high voltage, and they go around and around, of course. And of course he went to North Carolina in 57 and did a good bit of research there with J. Frank King. Now I'm going to put another picture up there just for variety, okay? That can keep you entertained while I just carry on about other things. That's where I live in North Carolina. That's where I do my research. Anyway, so Townsend Brown did a lot of research in North Carolina in Winston-Salem because that's where J. Frank King lived. They're both dead now. Townsend Brown died, I should have a date for that if you're interested. I think it was 85, October 27th, if I remember right. And J. Frank King just died last December, 89. Okay. So anyway, when I started this business, Dynamic Systems, it was for raising money to do this research. It's only taken about 15 years to get that together. It turned out to be a lead ball until it started making money. I've done other research too, just a matter of background, on electric harmonics in the solar system, and found some interesting things there. The purpose of that was to learn more about electricity. But there's some close relationships with planet distances and harmonic situations in earthquakes that are quite accurate, time-wise, not where they're going to happen, but when. That's never been published. I just have a pile of paper in there. And then, as was mentioned earlier, I did do the lightning research, and I did it with that ball on top of the house, hooked up to a digital, not a digital, but an analog storage scope. And that was in search of earth resonance, electrical earth resonance. And it was a matter of collecting lots of lightning signatures when the storm was going on nearby, within a few miles. Got too close, I shut down. Except once I didn't, and that took care of the scope. But anyway, that was back in 83 and 84. And I continue to do that. I have a new scope, by the way. It's a nice one. I love it. It's a Philips Fluke scope. And I can show you some of those lightning signatures that are... I won't dwell on those, but I will show you that this is a continuing activity. And maybe some of you aren't very familiar with... Pull that down just a wee bit. Maybe some of you aren't very familiar with what lightning signatures are like. Well, that top one is 1/10 of a second per grid square. So you've got a whole second there of time from one side of the screen to the other. Nice thing about this scope is you can get a nice long lightning trace, and then you can magnify the different sections and look at it, and that's what's going on down here. But in lightning, you're looking for resonance, you're looking for time periods, you're looking for pulses, and you can see them quite clearly. There, 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 there. There, there, there. You measure the timing between those pulses. And what I have found after doing that many times is that they fall into very discrete time frames, time spaces. Statistically, they really do fall into what would amount to resonant periods. And I talk about that in the paper I gave in '84. Just as a matter of variety, I will show you a couple of these other traces. That's a continued expansion of that first trace that was at the top of the picture. And you can see, you can really magnify them up. This will display dots also. It's not showing that on here because I didn't do them in dots for the pictures. You can see the variety in lightning traces, and they have distinct characteristics. You've got the type that pulses. You can't see that too well at the top, but you can see it's a series of just pulses and decays. And you have the type that has more of an extended voltage field pattern. And you can see they can cover a wide variety of shapes. And they represent different types of lightning bolts. Okay, let's see here. Okay. The point of all that is there are discrete time periods between each of these peaks, and they are consistent, and they are pretty much certain time periods. They're not scattered all over the place. Okay. My current scope obviously does a lot more than my earlier one did, but I've never published anything more about that. I'm going to just put a little slide on here about Townsend Brown. This is a very elementary sketch of the kind of experiments he was trying. This basically is the one that was in Los Angeles. But he tried the capacitor type. Those that are not familiar with it, basically a capacitor hung on a parallel wire where he measured the movement back and forth over long periods of time. This all ties in with spacecraft. It's just there's an awful lot of detail work to go through before you build something, right? There's a in terms of electricity, there's a couple of good books out. I haven't heard mentioned, but one of them is called Einstein Plus 2, and it's a very fundamental look at electricity from Maxwell to the current time. But it's showing basically that you don't need relativity to come up with all the present-day modern quantum mechanics, etc. It's done very much detail, and it does cover things like gravity and planet. So it's a very broad book on electricity. Okay. Oh, it's the author is Peter Beckman. Golden Press is the publisher. It's 1987. It's hard to get a hold of, but it's a current book, obviously. So we're going to talk about the Searle primarily. And what we'll do after that, I'm going to cover the Searle just generally, because I'm getting the idea of, just from talking around earlier, that there's a good many people here that aren't really familiar with what he did and what the claims are. But I'll try not to bog down on that, because there are some good books in the bookstore about it, like Rho Sigma especially, and there's no need for me to reinvent the wheel. Okay. This is a very general schematic, and those of you that aren't familiar, the Searle generator is basically supposed to consist of 3 rings. And the reason it has some excitement about it is that it's a concentric charge generator, meaning that the center goes positive and the outer edge goes negative. This is different from most generators, with the exception of Faraday generator. But basically you have a fixed inner ring, which is the dark one here, and you have a center ring, which is driven, and then I understand there's an outer ring that would be free to rotate. Although I've talked to some people here and they've given me some other variations, there's a lot of speculation about just how this thing is really made. Very few people around here seem to have good information, direct information. But the idea being that you have a transport mechanism here in the center ring, which is driven, which puts charge on the outer ring, very high voltage charge, millions of volts. And the top and bottom skins, this is a disc-shaped generator. The top and bottom skins collect charge like a capacitor, and my understanding is it's the same charge, top and bottom, and the outer rim is negative. My understanding is the top skin is some non-magnetic conductor covered on both sides by insulators. Some of the odd things about this is that it apparently, once it gets up to a certain speed, will start self-generating, and until it breaks loose from its foundation, it takes off. Couldn't prove it by me.
Can you scoot that picture up so we can see the bottom of it?
Sure can. Okay now? Okay. This is a little more detail about another variety of how this thing is made. That fixed ring in the center is supposed to be a magnet or an iron material, even if it's not magnetic, I guess. But one of the unique things being that it has these roller magnets that roll around that center ring. And in this configuration, you see the idea that the roller magnets are going around that center ring, and the charge is developed there and collected by this brush right here. As I show it there, it's showing that it's these roller magnets are going to stick right to that center ring without any other support other than their magnetic fields. Let's see. This one was said to generate 30,000 volts. It's supposed to have had an air pressure decrease at the center, and the center got colder, and objects in the center lost weight. I'll raise that up a bit so you can see the bottom. At first, the top one just showed rollers going around. It's my understanding that's how the top one was. But later versions got into 3 rings. So you'll find that most of the vagueness about this design has to do with what the magnets were made out of, how the rings were structured. They're supposed to have been segmented. What the shells were made out of. The only thing that seems to really come across consistently is that it produced a very high voltage, and that its center was positive and the outer edge was negative. With such vague reports on just what was happening there, I decided I had to research that thing. I'm going to skip along here a little bit and get into some of the experiments that I did that have to do with trying to figure out what's going on here. I have glossed over the structure pretty much because there are scattered papers around and books out that describe some of this, and some of that is in the bookstore currently. I'm going to describe one of the characteristics that was mentioned is that the center ring had an ionized field or a flame barrier between it and the next ring out. So I did just a little bit of experiments with high voltage and flames. Now this is about 10,000 volts DC. Normally that would give about maybe ½ inch or 5/8 spark. It's just a transformer, a DC transformer. And I found I could get the spark to go 3 inches. What I did, I took 2 propane torches and I connected the plus and minus terminals to the metal exhaust of the torches. And what you can see there basically is you still get a spark. I thought maybe it would short out, but it doesn't short out. You still get a spark. Here's a little bit here. It goes across, across. It actually snaps through that flame. And it can go up quite high. Those snaps can go way up here sometimes. I'm not sure what that meant exactly, other than I was just curious what that might have to do with what Cyril had been reported about Cyril. I want to do some more high voltage DC stuff, so I did, just as a matter of passing interest, built a Wilmhurst, and then of course some Tesla coil stuff and other discs that I use for rotation. Now, one of the things Cyril started out saying was, if you just simply rotate a ring, you could get a negative voltage on the outer edge of the rim. This particular disc up here, of course it has a magnet around it, but I did it without magnets also. That's a classical Faraday disc setup right there, which works, and it's a strong magnet. But if I just spun that disc without any magnets around it, I did indeed get a negative voltage around the rim. The odd part, I thought, was that it was confined just pretty much to the edge of the rim. It was only maybe 30 millivolts, 40 millivolts. But another odd, when I say it was confined to the edge, I mean it was only reading that voltage, say like the outer inch. If you move your measurement in closer, you lost your voltage. But another odd thing was, is right on the very outside rim edge, the voltage went practically to 0. And then if you lifted your probe just off of the edge of the disc, it would go to a positive reading. I have an idea that there's a lot of electrostatic charge being built up just by the surrounding air. Pardon?
You're measuring between the two sides?
Yes.
Where's your return?
My return was to the shaft. But I pretty much, and I did that with my digital meter, which is a Fluke 77, which is a pretty good digital meter. And I also did it with the scope. And they agreed, except the scope showed things that were real hashy, because if I touched the rim to read voltages, of course I was getting intermittent contact, and it was real hashy. But I also did another thing with my digital meter, which you really shouldn't do, but I did it anyway. You take one of the leads and you swing it around like a rope, and you can get these voltages too that way. And I decided it must be static charge in the air that's causing that. I don't know that to be a fact, but that was my thought about the matter. I also did what Tom Baloney did. Set myself up a rotating magnet and disc, copper disc. These were small though. I just wanted to, again, I was just wanting to see what voltages would develop. And I'd get 50 millivolts is the maximum I ever caught. It would vary up to 20 to 50 millivolts. And you see here, what you're seeing here is a rotation, 1 revolution time. And those hashy things are really poor contact. And the reason they're separated like that is because apparently I was missing contact each revolution for a part of the revolution. Obviously, I'm showing my lab notes. I never have time to do a whole lot. We'll move along with this. Get into some of the more interesting stuff. I did the disc with and without magnets, magnets rotating, which only produced millivoltages. The Faraday disc did much better, of course. It was a stationary magnet around the disc. The disc itself was rotating. But then I started going to the Searle stuff, which was segmented disc. You have to realize there was very little information about Searle. I'm living up there on that mountain. And I'll describe that. This was a 12-inch diameter plexiglass disc. And it has 12 metal foil segments, ½ inch by 2 inch long, glued around the outside edge, as shown. And I was again going to do the same kind of thing. I was going to measure the voltages. So as this thing rotated, and I could touch this with my. Actually, I had a wire brush connected to my scope, and the other terminal was to ground. To ground and scope ground. But you can see I got this periodic cycle again. That's because of the RPM of the motor. We're measuring RPMs. But each of these is caused by a segment. Again, it's because I wasn't maintaining contact, that I didn't have this continuously. That's without anything, no magnets, just simply foil segments going around. That's when I touched it directly, I would get that. And when I held a wire with insulation on it parallel to the disc, meaning running parallel to the segment, without touching it, of course, I would get an induced voltage. Apparently there was a little charge on there. Very similar. Charge on there was very similar to what I got from the solid disc. Anywhere from 20 to 50 millivolts. Except it was pulsing, of course. Okay. I can show you a photograph of those squiggles. That's on the scope. That's 10 milliseconds. 10 milliseconds per radical square, and a 2 volt per radical square. So you can see it's oscillating about plus or minus 2 volts. Let's see, it's around 357 to 400. It ran in that range. I'll raise that up because that's the topic of our conversation for quite some time now. What you see here is that plastic disc with the aluminum segments on it. I'm walking on top of my wire. These segments. What you see here are two ceramic magnets, North Pole to South Pole, joined by an iron bar loop to pull them together. And those segments rotate through that field. And there's no contact, meaning there's no contact. The segments just go through there. And okay. Yes?
Lower your microphone a little bit, and then there won't be that feedback.
Like down here?
Yeah, I think that'd be good.
How's that? Does it sound okay?
Yeah.
Okay, I'll hold it there. Thanks. It wouldn't hurt to let me know when it's about 10 minutes from time to stop, because I can stop fast. This is just some lab notes, but what I'm wanting to show you here, because I didn't have the photographs to bring yet, is that, see the spikes? I'm starting to get spikes off of these segments. This is the setup I had. Here's the motor, the disc mounted on the motor, and the segments around the edge. And for the most part, I measured all my voltages outside of the magnetic field. I did not get in the magnetic field. I was just trying to see if I could get a voltage on those segments. I know it induces it. Well, it's in the magnetic field. Well, I did. You were wondering about the frequency. It's about 350 to 360 there. 357 average. Has to do with the motor RPM and the number of segments.
Were you using a high impedance scope probe?
Pardon?
Were you using a high impedance scope probe, like 10 meg?
Yes, it was 10 meg.
Is that 52 volts?
50 millivolts. Let's see, where are you looking? Over here?
Upper right. Upper right. Up here.
Oh, okay, yes, those are 50. That has to do with something we're not to yet.
Oh.
Because I was doing this without a magnet to start with. And when you did it without a magnet, you'd only get about anywhere from 20 to 50 millivolts. And then if you put the magnet in the field, you still only get 20 to 50 millivolts. If you put the magnet there. I mean, this is run without a magnetic field, with the magnetic field. And you still only got 20 to 50 millivolts. Now, the interesting thing is, let me get another picture here. Keep in mind, I'm trying to figure out why Searle could say he got these high voltages out on the rim. Okay. The interesting thing is, when you put a brush in the field of the magnet so that it contacts the segment as it goes through the field, Now your voltages jump up to about 50 volts and even higher. What happens is you get an induced charge somehow here. You literally have a small Faraday generator section, but you've got something else going on because Faraday generators do not generate much voltage. But when you make a connection like that, you get these high voltage spikes, and they are that high. They can even go higher, as much as 70 volts. I just used the one set of magnets and that 1 RPM, and in fact the magnets were spaced apart by 4/10 of an inch, so there's not a real strong field there.
I don't see one copper brush there. Don't you have two, and where would the second one be? Where would you return it?
Okay. All that's happening there is I have a connection to the segment while it's going through the field. I have a connection to ground.
And ground is the shaft, motor shaft?
It can, in this case, it's to the motor. In fact, you don't even need to have the ground. You have to connect that wire to, I did it without the ground. I did it connected to the steel magnetic loop. It didn't make any difference. This, by the way, this thing is fastened to a wooden cable. So basically, we're totally insulated unless you deliberately ground it. With the exception, of course, the wooden cable has some degree of conductivity. Who knows what it is? The voltages and pulse, rise time being so sharp. Who knows what happens in that condition as far as wood goes. Could be a conductor already. But they're very sharp spikes. I put the scope up. I put the scope up to. I don't know what the sweep rate was on it, but anyway, I got a nice clear image of each spike. The brush hits the contact, and as soon as the brush hits the contact, it starts discharging. Discharges in 450 microseconds, basically. That's the time, just about the time it takes for the segment to go by the brush. Now, I was still puzzled. I'm still puzzled why I developed such a high voltage. Gotta remember to keep this microphone down in my belly button here. At first I thought maybe I was inducing some charges just from the house wiring, etc. I spent quite a bit of time sorting this out. This just shows you some of the computations I was working on to see what was going on. But those segments actually picked up that voltage when it went through the magnetic field. So when it went through the magnetic field, like so, and I would have my probe up here. Then these segments go whizzing through the air all the way around to the side where I'd touch it with a probe. And it would have that 50 volts on it. Where I am, and on those days, it's like 90% humidity. That was another thing that puzzled me. How was I getting a static charge that didn't just bleed into the air, going through the air like that? There was another little surprise I ran into. I don't know if I have it here. I'll talk about that. Let you see another slide while I'm doing it. Another surprise I ran into, and this kind of threw me for a minute, is that the voltage along the segment, the segment was 2 inches long radially, was different at the edge than it was on the inner edge. It was different on the outer edge than it was on the inner edge by about 30%, consistently so. And the way you could tell is by the spike height. This really puzzled me because, like I say, let me get that picture back. This is just more detail. Like I say, the voltage is induced here. It's measured up here, and I was still getting a difference in voltage across the metal plate, virtually, which shouldn't happen, of course. And I finally decided, because this thing is mounted on a plastic disc, that there was a charge being induced in the plastic, which was distributed according to the radial velocity. Obviously, the velocity out at this edge is higher than the velocity in here. So I decided the induced voltage, while going through the field, was lower inwardly to the radius and higher outwardly on the radius. So I calculated that, and sure enough, the voltage difference did correlate with the radial velocity directly. And so I can only assume that the charge stays on those little segments as it goes around, is because the plastic is maybe acting like an electret for a short period, staying polarized and maintaining that charge distribution. Well, this was truly an electrostatic machine, and I was getting high voltages, high enough to be like a Wilmhurst or a Van de Graaff or something. And so I decided, well, I'll just try to collect the charge on a metal bowl that I stole, borrowed. I don't have any more pictures. No, you're stuck with that picture. That's the last one. Too bad. Well, I did. It would collect a charge, but the spikes, when you see those spikes, you see they're only 450 microseconds until they bleed off once they're touched. And they were very weak and just coming from one magnetic induction. So I couldn't get much of a charge. I could only get about 1,000 or 2,000 volts on this metal bowl that I was collecting on. The way I did that, I put the bowl over the top. Came across about like so. I found that if I connected the bowl directly to the segment by a wire as it passed through, that I lost my charge on the segments. That was kind of interesting because I thought it would collect, but it just sort of apparently did something else. But if I didn't connect the segment with a wire, if I just put the bowl there and left the connection by air, I could collect this charge up to 1,000 or 2,000 volts, and I couldn't get more than that because I'm sure it was just bleeding off so fast from such a weak source of input. However, when I did touch the wire to the segment in the bowl, you could read the same signature coming off the segment, meaning that I was now getting the spikes on the bowl. So literally, I guess it was just pulling that off of the segment, just feeding it, just like I had it touching the wire to it like before. The bowl was just another part of the conducting train. So when I set this up with more magnets and more powerful, this just shows you some of the computations I was working on to see what was going on. But those segments actually picked up that voltage when it went through the magnetic field. So when it went through the magnetic field, like so, and I would have my probe up here, and these segments go whizzing through the air all the way around to the side where I'd touch it with a probe, and it would have that 50 volts on it. Where I am, and on those days, it's like 90% humidity. That was another thing that puzzled me. How was I getting a static charge that didn't just bleed into the air, going through the air like that? There was another little surprise I ran into. I don't know if I have it here. I'll talk about that. I'll let you see another slide while I'm doing it. Another surprise I ran into, and this kind of threw me for a minute, is that the voltage along the segment was 2 inches long radially, was different at the edge than it was on the inner edge. It was different on the outer edge than it was on the inner edge, by about 30%, consistently so. And the way you could tell is by the spike height. This really puzzled me because, like I say, let me get that picture back. This is just more detail. Like I say, the voltage is induced here. It's measured up here, and I was still getting a difference in voltage across the metal plate, virtually, which shouldn't happen, of course. And I finally decided, because this thing is mounted on a plastic disc, that there was a charge being induced in the plastic, which was distributed according to the radial velocity. Obviously, the velocity out at this edge is higher than the velocity in here. So I decided the induced voltage, while going through the field, was lower inwardly to the radius and higher outwardly on the radius. So I calculated that, and sure enough, the voltage difference did correlate with the radial velocity directly. And so I can only assume that the charge stays on those little segments as it goes around, is because the plastic is maybe acting like an electret for a short period, staying polarized and maintaining that charge distribution. Well, this was truly an electrostatic machine, and I was getting high voltages, high enough to be like a Wilmhurst or a Van de Graaff or something. And so I decided, well, I'll just try to collect the charge on a metal bowl that I stole, borrowed. Any more pictures? No, you're stuck with that picture. That's the last one. Too bad. Well, I did. It would collect a charge, but the spikes, when you see those spikes, you see they're only 450 microseconds until they bleed off once they're touched. And they were very weak and just coming from one magnetic induction. So I couldn't get much of a charge. I could only get about 1,000 or 2,000 volts on this metal bowl that I was collecting on. The way I did that, I put the bowl over the top. Came across about like so. I found that if I connected the bowl directly to the segment by a wire as it passed through, that I lost my charge on the segments. That was kind of interesting because I thought it would collect, but it just sort of apparently did something else. But if I didn't connect the segment with a wire, if I just put the bowl there and left the connection by air, I could collect this charge up to 1,000 or 2,000 volts, and I couldn't get more than that because I'm sure it was just bleeding off so fast from such a weak source of input. However, when I did touch the wire to the segment in the bowl, you could read the same signature coming off the segment, meaning that I was now getting the spikes on the bowl. So literally, I guess it was just pulling that off of the segment, just feeding it, just like I had it touching a wire to it like before, The bowl is just another part of the conducting train. So when I set this up with more magnets and more powerful fields, it'll probably do all right as an electrostatic generator. But it is kind of unique. And it does show one way of, if this was just simply set up in disk form, of putting... Oh, by the way, the other strange thing about this is I could never get it to be anything but positive on the segments. I could switch the... I didn't change rotation, but I switched directions of magnetic fields. I even put north to north, south to south, things like that. And it still did the same thing. I don't quite understand that. Maybe Tom Bone can tell me about that.
Do you ever vary the RPM?
No, I just had a fixed RPM motor. Actually, I had a rheostat on it, but it was not a variable speed motor. So, I'm trying to think. Now, the ML generator, I guess, being like a modified Wilmhurst, did some things. I was thinking to try this with a Wilmhurst. I have that nice Wilmhurst I built. I thought I'd try that because I'm not aware of anybody trying a disc rotating with metal segments on it and then putting that brush attachment as it goes through the field to produce these voltages. And I'm just wondering if the Wilmhurst couldn't work that same way, to be modified that same way. Now this doesn't get us to the Searle configuration yet. It just gets us to the point of, well, okay, so you can produce a radio field generator, which is one of the requirements I'm going at, and at high voltage. So I think this could be configured with capacitors top and bottom, and it's going to naturally be one charge at the center and another charge around the edge, inherently from its design. He used rotating rollers in these, or I should say rolling magnets. And I've got the magnets and I've got the means to go ahead and set that up. I'll be setting that up pretty soon and test that out because that's really a neat something. And I'm going to have to try that. And of course, someone around here might save me a lot of trouble if they just tell me how it works. But that's the idea. How's my time looking?
You're out of time.
Okay, that's a good time to stop. I told you I could stop suddenly. Thank you.